First of all, good evening to all. My name is Ganesh Shankar Pandari, and I am going to take the live session for NPTEL course Municipal Solid Waste Management taught by Professor Ajay Kalamdar. And this is the fifth live session for the course for this course. So we are going to solve some new solve some problems based on the lectures delivered in the last week, week 5. So before going to the problems, we will briefly discuss about whatever uh, the content was shared with you in the last week. So in the last week, we have taught about chemical transformation of the municipal solid waste. So this is a very important factor in the municipal solid waste management regarding processing and transformation of that municipal waste. So that waste can be used as a fuel source because the municipal solid waste contains some dry materials like cardboards, paper sheets, or maybe sometimes woody materials also there. So those waste contains some calorific values, and those can be used as a fuel source. So the primary difference between waste incineration and other combustion system is that the waste incineration process treats incoming waste with great variations. Okay, so when we are talking about the waste as a fuel, okay, so if we are going to compare this waste material with the other fuel source like petrol or diesel or 100% woody material, because those materials are having some uniform nature and those are not going to change frequently. But in case of waste material, that waste material is going to change frequently. Okay, so the incineration process has to be designed in such a way that that non-uniform waste materials can be treated as a fuel source. So practical design limits allowable variations of waste composition, and according to the uh, some accord we have to uh, keep in mind some parameters like moisture content or organic volatile matter or fixed carbon content in the municipal solid waste, which has to be in the desirable range for treating it as a fuel source. Like moisture content has to be on the lower, always has to be on the lower side, less than, it has to be less than 45%, and organic or volatile matter has to be greater than at least 40%, and fixed carbon content has to be lower than 15%. Then only it can be used as a fuel source. On the other hand, there will be a lot of inert materials also will be coming in the municipal solid waste material, like debris or dust particles. So that has to be less than 35%. Okay, and that net calorific value of the waste has to be at least greater than 1500 kilo calorie per kg of waste material. Otherwise, if we are going to treat a municipal solid waste having a calorific value lower than 1500 kilocalorie per kg as a fuel source, then we will not be going to get the economy out of that process, because we also have to maintain the economy of the process. So there are some basic considerations before designing of the municipal solid waste as a fuel source. Best available data on the amount and composition of each waste type has to be generated. Effect of future change in waste management has to be taken into consideration, and how much amount of street sweeping, construction, and demolitions waste are coming in the waste material frequently. So that amount we have to be take into consideration, because they cannot be treated as a fuel source. Okay, they are finally going to report into the ash content, and they will not participate in the fuel source. They will not participate in the combustion or incineration process of the municipal solid waste management. Then there are some key parameters during the characterization of waste as a fuels. First is heating value. So heating value per unit weight or volume of combustible material that is going to be completely burned. Okay, so heating value is roughly proportional to the bad waste that is combustible, like including moisture and ash content, and add to the carbon content of the combustible reaction. Then moisture content, it is a critical parameter of the waste which is going to be treated as a fuel source, because if the moisture content is very high inside that municipal solid waste, then what is going to happen, whatever the energy which is going to produce during the incineration or combustion process of that municipal solid waste, it is going to release the moisture content in the vapor forms. Okay, so we will not get efficient heating value from the incineration of that municipal solid waste. So it has to be lower than at least 45%. Then coming to the ash content, the substance that is known as substance left after ignition at 550 degrees Celsius, that mainly contains the inert materials like street sweepings or demolition waste, if it is coming with the waste content, and sometimes some silica content or some glass content or some metallic content, if it is coming in the waste material, that will go into the ash content finally. So then coming to the heating values of the waste, some variables are used for determining whether a waste can sustain the combustion process without supplementary fuel. If we are going, there are two things. If we are going to incinerate that waste material, municipal solid waste material, then first thing is, if we have to provide some extra fuel material during the combustion of the process to provide efficient calorific value to produce some energy or some or use of that energy into something substantial. So if we are going to need some extra fuel material with the municipal solid waste or not, that will be decided on the basis of the heating values of that municipal solid waste. So there are two types of heating values which are taken, which we have to take into consideration. First is lower heating value. So lower heating value is like energy released upon complete combustion of a fuel, carbon to CO2. So carbon is going in to convert into CO2 gas, hydrogen is going to convert into H2O gas, and sulfur is going to convert into SO2. It is like complete oxidation of the materials present in the municipal solid waste, and water is evaporated, leaving the process in its evaporated state. Then coming to the higher heating value, energy is released at complete oxidation and water leaves the combustion process in its liquid state. It expresses a theoretical maximum energy released from the fuel. So it is like whatever whatever the energy has produced during the combustion of that uh, municipal solid waste, excluding the content of the water which is going to evaporate by that heating value itself. Okay, so that will be known as higher heating value. The difference between this higher H low and H high is the heat of condensation of the water vapor contained in the flue gas originating from moisture in the waste, and moisture generated by the oxygen of the hydrogen bound within the chemical structure of the waste. So with the help of these things, we can calculate the heating values of the waste material or calorific values of the waste material. So there are some formulas for the calculation of the higher heating values and lower heating values. So higher heating values can be calculated by the with this formula, which is H low plus water plus hydrogen content into 8.937 into 24.45 kilojoule per kg. While the lower heating value of the material can be calculated based on the chemical composition of the solid waste material, like carbon, hydrogen, oxygen, nitrogen, and sulfur content present in the municipal solid waste material. So with the help of that material, we can calculate the lower heating value of that municipal solid waste. So the term calorific value is often used instead of heating values. Net or inferior may be used for lower heating value, and gross or superior or upper may be used for higher heating value. So we can call lower heating value as a net calorific value or inferior calorific value, or we can call gross calorific value instead of higher heating value. So in India, generally we use gross calorific value terms and net calorific value terms instead of lower and higher heating values. So there is some numerical problem. So if we are going to consider 1 kg of waste with the following chemical composition, we have composition of carbon, hydrogen, sulfur, nitrogen, oxygen, chlorine, H2O and S content. So we can easily calculate the lower heating value, or we can say net calorific value, with the help of carbon, hydrogen and sulfur content, based on the empirical by using empirical formula discussed above. And after calculating the lower heating value or net calorific value, we can calculate the gross calorific value with the help of H2O and S content, with the by using empirical formula for the gross calorific value calculation. So coming to the next thing, so we can create some refuse derived fuel by using municipal solid waste. So according to this pyramid structure, we can see the most preferred the most preferred process for the recycling of the municipal solid waste is their reduction and reuse. Then we can recycle that waste, like we can recycle glass material, we can recycle cardboard material, or we can recycle metallic values from that waste material. Then we can go for composting process. After that recycling, we can go for composting process. After this composting process, if some material is still left behind, some dry material is still left behind, then only we will go for waste to energy conversion process. So we can see the waste to energy conversion process is the least preferred process during the management of municipal solid waste. Or after that waste to energy conversion process, whatever is left behind, like demolition waste or inert waste, is left behind after that waste to energy calculus conversion process. Or we can say during that waste to energy conversion process, whatever the S content is produced, that can go for landfill process. So refuse derived fuel is in integrated solid waste management hierarchies on the lower position. And the quality of RDF produced per ton of MSW varies depending on the type of collection, pre-processing and composition of the waste source. Okay, so that will depend on the carbon, hydrogen, nitrogen, sulfur content, and that will vary according to the waste composition. If waste composition contains higher amount of dry waste containing like cardboard or paper waste, or like leaves and some woody material, that waste can be converted into high value refuse derived fuel, because that will be having very much higher calorific value. Otherwise it can be converted into low calorific value, that will be no use to the further processing plants. So utilization of refuse derived fuel, it's like Indian, if we are going to utilize this RDF. So where we are going to use this RDF content, we can go for some industries like waste to energy conversion process or power plant processes or power plant, or we can provide them this RDF to some households which are using RDF, which can use RDF material as a fuel source. So there are some net calorific values of the other heating sources in comparison to the RDF. So Indian coal generally have a net calorific value of around 2500 to 5000, and mixed plastic material have a net calorific value of around 6000 calorie. And RDF produced by the segregated municipal solid waste, which mainly contains plastic, cloth, jute, paper, or multi-layered polythene or multi-layered packaging material, that will be having a that is going to have a net calorific value of around 2000 to 2500 calorific value. So we can say the Indian coal is also having a net calorific value of 2500 to 5000 calorific value according to the S content present or fixed carbon values present in that Indian coal material. So we can use this RDF material as a fuel source in the power plants, generating power plants using Indian coals as a fuel source material to produce steam, and by that steam we can produce the electricity. So there is one case study in Gazipur landfill, which is located in the New Delhi, that have a waste that receive around 2000 ton per day waste per day, and that facility initially started to process around 13,000 per day to generate 4333 TPD of RDF, which was utilized for generation of 12 megawatt power with the help of power plant. The public private partnership PPP operator is infrastructure leasing and financial services. It provides a scientific solution to address some of the environmental health and safety hazards posed by the 29-hectare dumping ground, which is used as a landfill site containing 12 million tons of accumulated garbage. And then one more plant is there in India, which is located in Hyderabad, which is also using RDF as a fuel source to produce 11 megawatt electricity in the power plant. Then coming to the so either we can convert that waste material into RDF material to use as a fuel source. Then after converting them into RDF, we can go for incineration or combustion process. Okay, so what is incineration process? The incineration process is basically defined as a combustion of waste at very high temperature in the presence of oxygen, and it will result in the production of ash, flue gas, and heat. So that heat can be utilized to produce steam, and that steam can be used to produce that steam can be used to produce the electricity. So and that incineration process can help to reduce the landfill volumes of the municipal solid waste. So there are some incineration process generally contains combines some generally contain generally combine some equipments, like we need a furnace for the combustion process, and in a furnace the combustible components react with oxygen of the combustion air, releasing a significant amount of hot combustion gas, which will be having a temperature of around 500 to 800 degrees Celsius or 900 degrees Celsius, and that temperature can easily convert the water into the steam in the with the help of a boiler, and that steam can be converted into the that steam can be used to produce the electricity in the power plants. So the combustion gas pass from the furnace to the after burning chamber, and as per European Union, a minimum temperature of 850 degrees Celsius for municipal waste and 1100 degrees Celsius for certain types of hazardous waste have been set for the complete burnout of combustion gases in the after burning chamber. As per EU, the above temperature should be maintained for a minimum time of 2 seconds as measured from the last injection of the combustion air. Then coming to the brief history of the waste incineration, waste incineration. The first incinerators developed in the United Kingdom in the 19th century for the municipal solid waste management. The waste incinerator plants treat waste of great variation in composition, and moving grade technology was developed in 1920s and 1930s and developed as a combination of grade with rotary kiln in few years thereafter. So there has the waste incinerators has gone with some changes in the technology, like first we were using the static waste incinerator, then we have gone to great incinerators, and then we had gone to the rotary kiln incinerators type. Then we have utilized some electrostatic precipitators process to remove most of the dust from the flue gases by 1970 and 1980s, and in the 1990s we have uh, incorporated the after combustion chamber. Okay, so that after combustion chamber can utilize after combustion chamber can burn out the gases which is having some calorific values, like if this waste incinerator is going to provide the CO gas. Okay, that CO gas is going into the flue gases, but that CO gas is still having some calorific values that can be converted into that can react with the oxygen gas to convert into the CO2 gas. So we have incorporated some after combustion chambers to utilize this calorific value and converting this CO gas into the CO2 gas at some around 850 to around 1100 degrees Celsius temperatures. Then we have to provide some pre-treatment processes before going for the combustion process. So depending on the quality of the waste and incineration system, some pre-treatment techniques may be necessary, which mainly involve sorting and homogenization of the waste before incineration process. So the mass burning incinerator parameters are removal or shredding of bulky or heavy items, then mixing of low and high heating value waste, because we have to maintain a net calorific value of around 2000 to 2500 kilocalorie per kg of waste material. Otherwise, it will not be economical to uh, produce the to use the RDF material as a fuel source in the power plants. Then for homogeneous waste pre-treatments for homogenizing the municipal solid waste, some pre-treatments are shredding for homogenize. We can shred the material into some smaller pieces so that we can easily homogenize the municipal solid waste. Then we can screen for narrowing the particle range to the fluidized bed, and we can remove the metallic iron with the help of magnets or some other magnetic material with the help of eddy current process, eddy current separator, or with the help of cyclone separator or air cyclone separators. We can easily remove the metallic iron content or some metallic content, or we can say some glass content which we don't want to we provide we which we don't want to which we don't want to be interfere in during the incineration process of the municipal solid waste. So there are some types of there are different types of incinerators which are commonly used in the industry for the combustion of the waste material, or RD, or we can say RDF, or we can use the coal materials also in these incinerators as a to convert these fuel source into the high temperature flue gases, and that flue gas will be used as a source for the heating material, will be used as a heating source for the water to convert into steam. So there are some different types of incinerators like moving grate incinerators. Then coming to the next, so in this moving grate incinerator, what will happen? We will be having a conveyor belt. That conveyor belt is going above on a furnace having some temperature, and we are continuously purging the oxygen gas into that incinerator. So these RDF material or municipal solid waste material is going to combust and provide going to combustion, and after combustion they are going to convert into the gaseous content. So there are some advantage and disadvantage of these moving grate incinerators. These types of incinerators can accommodate large variation in waste composition and in heating values. Can be built in very large units, like we can build a incinerator up to having a capacity of up to 50 ton per hour. And there are some disadvantages also, because these types of plant installation cost is very high, and then maintenance cost is also relatively high, so we cannot match up with the economy of the whole process. Then second type of incinerator is rotary kiln incinerator. So in the rotary kiln incinerator, as suggested by the name rotary kiln, so this is having a drum type incinerator which is going to rotate at some and having some angle around 5 to 10 degree, as can be seen in the image. This is having a some angle of around 5 to 15 degrees, 15 degree, and it is going to rotate in the anti-clockwise or maybe clockwise direction depending on the process. And from this direction we are going to provide the oxygen to for the proper burning or proper combustion of the municipal solid waste. So the diameter of the cylinder can vary from 1 to 5 meter and length can vary from 8 to 20 meter, and the capacity should be within the range of around 2.4 ton per day to 480 ton per day. It will be having lower as compare it will be having lower capacity as compared to the moving grate incinerator, which can have a capacity of around 50 ton per hour, but these rotary kiln uh, incinerator can have a maximum capacity of around 20 ton per hour. The kiln rotates with a speed of typically around 3 to 5 rotations per hour, and the axis air ratio is well above that of the moving grate incineration and the fluidized bed reactor. So the energy efficiency cannot exceed around 80%, cannot exceed more than 80%, as the retention time of the flue gas usually is too short for complete reaction to take place in the rotary kiln itself, and the cylinder is followed by an after burning chamber. So we have to provide a after burning temperature chamber having a temperature of around 850 to 1100 degrees Celsius, which may be incorporated in the first part of the boiler. The rotary kiln may also be used in a combination with a moving grate, where the moving grate forms the ignition part and the rotary kiln forms the burning out section part. So there are some advantages and disadvantages of the rotary kiln. Rotary kiln can be regarded as a mostly similar to it is mostly similar to the moving grate incinerator, and energy efficiency is lower than the moving grate incineration. Like moving grate incinerator can have a energy efficiency of around 95 to 96%, while the energy efficiency of the rotary kiln cannot exceed beyond 80%. And there are some disadvantages of the there so the advantage there are these were the disadvantages of the rotary kiln, and the some advantages of the rotary kiln are the plant installation and maintenance cost is very lower as compared to the moving grate incineration, and rotary kiln may be rarely used for new MSW incineration plants with high heating value waste. So the third type of incinerator is fluidized bed incinerator. So in the fluidized bed incinerator we can go with the lower size particles. The particles which is having very lower size, we can go with the fluidized bed incinerator. So the incinerator works on the principle where solid particles mixed with the fuel are fluidized by air. So they will be in the fluidized condition. By fluidization, the fuels and solids are suspended in an upward air stream, thereby behaving like a fluid. This reactor usually consists of a vertical refractory lined steel vessel, like we can see in this figure, containing a bed of granular material such as silica sand, limestone, or a ceramic material. So the fluidization of the bed is ensured by the air injection through a large number of nozzles in the bottom of the incinerator, causing a vigorous agitation of the bed material, in which the incineration of waste takes in the place in close contact with the bed material and combustion air, allowing relatively low excess air level and high thermal efficiency up to around 90%. So there are some disadvantages and advantages of the fluidized bed reactors, like reduction of dangerous substances in the fluidized bed reactor can be easily done. Flexibility regarding low quality fuels and cost, etc., and NOx generation may be low due to relatively low and well controlled combustion temperature. So we can control a combustion temperature of around 900 or 1000 degrees Celsius itself, and the NOx generation can happen over around 1300 or 1400 degrees Celsius. So the burnout of flue gas and particle is usually good due to long residence time of the flue gas in the free board above the fluid bed, and capital and maintenance costs are relatively lower as compared to uh, moving grate incinerator or uh, rotary kiln incinerator. So there are some disadvantages also, like demanding pre-treatments are required for smooth functioning. As we have already discussed, these types of fluidized bed reactors, demands lower size particles. Like the particle size cannot be bigger than around 1 mm or 5 mm. So that it can easily fluidize with the help of the air. If the particle size is much bigger, around 15 or 20 mm, or we can say around 1 inch or 2 inch, so the we have to provide more and more pressure of the gas from the bottom to keep it in the to keep the particles in the fluidized conditions. So it demands some pre-treatment process for smooth functioning of the process, primarily used for homogeneous waste types, which included liquid waste too. So in the fluidized bed reactor, we can use liquid waste also during the incineration process. Then these are the moving grade incinerators, and then so how the energy recovery system works. Okay, so the first we are going to incinerate the municipal solid waste or RDF generated with the help of municipal solid waste, and the gases generated during the incineration of the solid waste are going to leave the furnace at a temperature of around 1000 to 1200 degrees Celsius. And then these hot flue gases are cooled using boilers before passed on to flue gas cleaning system. So with the help of these boilers, what we are doing, in these boilers we are creating steam with the help of the flue gas temperature at of around 1000 to 1200 degrees Celsius. And during this process, what will happen, these flue gases are going to transfer their temperature to the boiler, converting the water present in the boiler into the steam, and that hot steam is going hot steam is to be used as generating power in the power plants. So during this conversion from water to steam, the temperature of the gases is going down from 1000 or 1200 degrees Celsius to around 100 or 200 degrees Celsius. After that, these flue gases having a temperature of around 100 or 200 degrees Celsius, these will go for a gas cleaning system to recover any suspended particles in these in these flue gases, and after that flue gas cleaning system we are going to release them into the environment. So summary of typical efficiencies in different energy recovery systems. So if we are only going to heat it, so energy recovery will be at around 75 to 90%. Then we are going to convert that heat into the steam. So that recovery efficiency will be at around 75 to 90% itself. Then this steam is going to be utilized to convert them into the power. So this power conversion will be having a efficiency of around only 25 to 35. So overall efficiency will become down to around 25 to 35%, and then combined steam and power can have a overall efficiency of around 75 to 90. So now we will go with some case study. So India's first waste incineration plant was established in 1987, and it has gotten failed. It has not worked. Okay, and it was commissioned by utilizing a capital cost of around 20 crores, which was imported from Vlaun Military Limited of Denmark. The plant was designed to, why this plant has failed? Because the plant was designed to uh, incinerate 300 tons of municipal solid waste per day to generate around 3.75 megawatt of electricity, and it was designed to incinerate a municipal solid waste having a calorific value of around 1462.5 kilocalorie per kg, or around, we can say, around 1500 kilocalorie per kg. But the calorific value which was uh, the calorific value of the municipal solid waste which was supplied to the plant in those days was only having a calorific value of around 600 to 700 kilocalorie. So attempt to supplement the combustion with diesel fuels. In order to maintain a calorific value of around 1500 kilocalorie, they have implemented the diesel fuel as a supplement material, which but it has also gotten failed, and the ministry incurred an expenditure of around rupees 1.25 crores on the maintenance and insurance of the plant, and the project was officially shut down in the July 1990 because we were not able to provide a sufficient we were not able to provide a municipal solid waste to the plant, which is having a calorific value of around 1500 kilocalorie, and it was not economical to incinerate that 600 to 700 kilocalorie municipal solid waste into that plant. So the project was officially shut down in July 1990. So coming to the next chapter, we have incinerated we have already incinerated, or we can say combusted, the municipal solid waste or RDF fuel. So after that RDF fuel, what we have done, we have used the heating value of those gases to convert the water into the steam, and that steam can be utilized as a fuel, as a uh, energy generation source. So what will happen to that flue gas? So that flue gas has to be passed with some treatment, and then only we can leave it in the environment, because that flue gas can contain some hazardous elements like fluorine or bromine, or sometimes it can contain some CH4 or CO values also. So that has to be treated. So during the combustion, we are going to have different types of products, like we can get some mineral materials in the form of ash content. We can get carbon, hydrogen, sulfur and nitrogen gases. We can get some halogens like chloride or bromide, and we can have some volatile heavy metals also. In the high temperature and oxygen surplus present in the combustion chamber, all input species are converted into the most chemically stable product under oxidizing conditions. The product either enters gas phase or remain as solid residues in the fuel beds. So mineral materials as well as a lithophilic heavy materials can include iron, manganese, titanium, nickel and their compounds leave the combustion chamber as bottom ash at the back end of the grate, and carbon, hydrogen, sulfur, that can convert it into some stable oxidation product, like all of carbon is going to convert it into CO2, H2, hydrogen into H2O, sulfur into SO2, and nitrogen into NO2 or N2O, depending on the temperature provided during the combustion process. And depending on the operation mode, more or less particulate matter leaves the furnace as dust, which can also known as fly ash or in the flue gas form. While the incomplete combustion of the carbon leads to the formation of CO, TOC, polyaromatic hydrocarbons and soot particles, and these soot particles are known to be a source of toxic low volatility halogenated organic micropollutants, especially PCDD or fluorides. These halogens are transformed into the respective halides, like the chlorine can be converted into the major product is gaseous HCl, or 10 to 15% of the chloride stays as metal chloride in the solid residue, while the bromine can be converted into the HBr and metal bromide. And fluorine is going approximately 70 to 80% of fluorine is going to converted into the fluorides like HF gas or in the solid part. And the volatile heavy metals, though these can be mainly evaporated as chlorides in the furnace, more than 80% of the content of mercury and cadmium in the waste leave the combustion chambers in the flue gases. So we can say the flue gases which is going to leave the furnace or combustion chamber will be having a higher quantity, will be having a sufficient quantity of mercury, cadmium like heavy metals, HBr, HF gases or HCl gases, and some soot materials like CO or CH4 or some unburnt hydrocarbon. So the uh, treatment of these gases is unnecessary. So 30 to 50% of zinc, arsenic, antimony and lead, which are heavy metals, is evaporated in the combustion chamber and transferred to the raw gas. At the typical boiler outlet temperature of around 180 to 200 degrees Celsius, all volatile heavy metal species except mercury and its compound are bound to particulate matter and are removed along with the dust in boiler and filter assays. So the flue gases will be containing about 80% of the waste is transferred into the flue gas during the waste incineration process. Most problematic content in the flue gases are dust particles, acidic gases like HCl, HF or SO2, NOx emission in the form of NO2 or it can be in the form of N2O, heavy metals and the organic pollutants like dioxins, furans and PCDD or fluorides. Flue gas must be extensively cleaned before being released to the atmosphere through the stack of the plant. So there are some flue gas cleaning system uh, which includes flue gas cleaning system is required to reduce the concentration of specific pollutants as we have discussed earlier to concentrate well below the respective air emission limit. So there are four specific type of pollutants which needs to be cleaned from these flue gases before leaving these flue gases into the environment. One is first is dust particles, then acid gas like HCl, HBr or HF gases, then pollutant and harmful compounds like dioxins, furans, and NOx. So there are some equipments which needed during the treatment of these flue gases. So first is induced drought fan. So why we are using this induced drought fan? What it will do? It will ensure that no polluted flue gas escape from the process equipment by providing a reduced pressure therein. What it is doing? It is going to provide a reduced pressure, and due to that reduced pressure in the chamber, what will happen? The flue gas will flow from the higher pressure to the lower pressure part, and from that lower pressure part we can transfer those gases into the dust removal systems like cyclone or like air cyclone or water cyclone systems to remove the dust particles from these raw gases. And after the removal of these or we can uh, go with the electrostatic precipitators for the removal of the dust particles. If the particle so what is going to happen in these electrostatic precipitators, we are going to provide some negative or positive charge to the dust particles and to the plates provided into this electrostatic precipitators, and due to the opposite charge what will happen, the dust particle will be attracted towards these plates, and due to that attraction these will incorporated on the plates itself. And when we are going to release the charge from the plates, what will happen, the dust particle incorporated on the plates are going to remove down and we can collect them. So the removal efficiency of electrostatic precipitators are very high, around 95 to it can work up to with an efficiency of around 95 to 99.5%, and the operating temperature of the gas flue gases can be operated up to a temperature of around 400 degrees Celsius. Or we can go with the fabric filters because ESP precipitators are very costlier process. So we can go with the fabric filter process also to remove the dust particles from the flue gases with the help of the fabric filters. So what we are going to do, these fabric filters are going to have some porous structures on these fabric filters. These are going to have a defined porous structures, and we are going to uh, pass the flue gases from these fabric filters. So what will happen, according to the pore size, the dust particles are going to add is going to incorporated in these fabric filters, and the gas is going to be passed from these fabric filters easily. The removal efficiency can be up to 99 to 99.5%, and the temperature of the gases which can be feed into these fabric filters can be up to 250 degrees Celsius. Then we can also use Venturi scrubber. It is like same as the cyclone separator process, or we can go with the acid gas scrubber system. With the help of Venturi scrubber, we can provide some wet system, like we can sprinkle the water on the waste gases. So what will happen? Whatever the HCl gases or chloride gases is coming from in these flue gases, these are going to react with the H2O, which we are going to sprinkle in the acid gas scrubber system. And with the sprinkling of this water, the chloride gas is going to react with the H2O, and it is going to get converted into the HCl acid in the liquid form. And that HCl acid can be collected at the lowest part and can be refined again to be used as a industrial acid, or can be refined to be used as a laboratory grade or analytical grade reagent. So during the process, during the process acid during the gas cleaning process itself, we can generate a byproduct also in the form of HCl or H2SO4, depending on the gases produced in the uh, during the incineration process or combustion process. So we can also go with some dry systems, like with the help of CaOH or NaHCO3 are injected into a flue gas for neutralizing of the acidic gas component. So what will happen? These acidic gas components are going to react with the calcium hydroxide or sodium bicarbonate powders, and the gases are going to be neutralized. Then the dioxin and furans can be present in the MSW, but they are almost totally destroyed in the combustion chamber. In the boiler at temperature down to 200 degrees Celsius, a new formation takes place. This is gaseous PCDD can be absorbed on the activated carbon. We can use some activated carbon filter or some bed filter, or in a carbon injection system to catch these dioxins and furans before uh, leaving the gas to the atmosphere. And the nitrogen oxides NOx removal is the common terms for nitrogen oxide and nitrogen dioxide in waste incineration plant. More than 95% of the total NOx in the flue gas is present as NO. If the combustion process is drops below 850 degrees Celsius, an increasing fraction of NOx is present as N2O. N2O has an extremely high greenhouse gas potential of 310 compared to 1 for CO2. And that NO or N2O has to be converted into the nitrogen with the help of some oxidative environment during the flue gas treatment processes. Now coming to the next lecture, solid. So we have discussed about the gaseous generation during the combustion process. Now, along with these gaseous generations, some solid residue is also going to generated during the combustion or incineration process. So we have to characterize that we cannot leave that solid residue as itself. We have to characterize that solid residue, and we have to provide proper treatment to that solid residue content. If we can recover something from that solid residue, or we can go with the landfill for this solid residue, or we can uh, use this solid residue as an inert material, or we can use this solid residue like fly ash or bottom ash content as a cement, as a raw material for the cement making, which because these residues generally contain high amount of silica material and sulfur, some amount of silicon sulfur materials also. So there are different types of residue which are generated during the incineration process. One is bottom ash, which is also known as slag material, then grade shiftings, boiler ash, economizer ash, fly ash, and acid gas cleaning residues. So the bottom ash is formed during the formed and transport through the combustion chamber on the moving grate and sometimes through a rotary kiln to the quencher. When the bottom ash leaves the grate or rotary kiln, it must be cooled. Uh, this bottom ash mainly contains materials that is removed from the flue gas at the cooler surface of the boiler and other heat transfer equipment. So the material that condenses on the surface act as an insulator, reducing heat transfer rates, and must be removed at regular intervals to maintain proper efficiency. Then coming to grate shiftings, the pass through the openings in the grate, either due to the size or because it melts and is trapped in the under fire air plinths located below the grate, is referred to as grate shiftings. Then economizer ash is known as finer particles collected from the flue gas in the economizers or economizer hoppers installed in some boiler systems to optimize the recovery of heat from the flue gas before the gas is subjected to a more thorough treatment. Then fly ash, it is basically catched during the treatment of the flue gases. Relatively fine, it generally contains relatively fine ash particles around. The size can be around 5 micron to 10 micron or 15 micron, something like that. Entrained in the flue gas from the boiler and recovered in electrostatic precipitator or fabric filters. So that is generally known as fly ash. Then coming to acid gas cleaning residue, the solid residue and or waste water generated during the treatment to remove acid gases from the flue gases known as acid gas cleaning residue. So the typical amounts of various residue produced per ton of waste incinerated in modern state of the art mass burn incinerators generally contains 150 to 300 kg per ton amount of bottom ash. Then grade shiftings can be around 5 kg per ton, boiler ash 5 kg per ton, and then fly ash generated can be around 10 to 30 kg per ton. And then coming to the flue gas cleaning residue, the dry process can produce flue gas cleaning residue of around 20 to 60 kg per ton, because it will also contain the amount of calcium hydroxide or sodium bicarbonate provided as a dry source to catch the uh, flue gas or to neutralize the flue gas. Then semi-dry process then can produce around 15 to 50 kg per ton, and wet process can produce around 0.5 to 3 kg per ton of the material in the form of sludge or in the form of gypsum. In the form of gypsum, it will be produced in the form of gypsum if we are going to sprinkle the water which is containing calcium hydroxide content. So what will happen, that calcium hydroxide is going to react with the SOx or chloride gases during the wet cleaning process, and that calcium hydroxide is going to convert into the calcium sulfate hydrate. So that will be known as mainly gypsum content. Then if we are going to characterize this residue, so it will mainly contain the amount of silica and silica, calcium and iron, silica, calcium, iron and aluminium in a range of around 50 gram per kg of around aluminium, Fe and calcium, and major amount is silica around 240 to 300 kg, 300 gram per kg, and there will be some trace amount of magnesium, sulfur, phosphorus, copper, depending on the chemical composition of the waste material which is going to be incinerated. And then coming to the composition of chemical composition of the fly ash, we can see it mainly contains silica and calcium around 1 1.6 lakhs mg per kg, or we can say 1.6 million 6 parts per million. Then it can also contain some heavy metals in the trace amount around 800 to manganese content can be around 1300 ppm, or PV content can be around 11,000 ppm. So it will be the chemical composition of these fly acids will mainly depend on the initial chemical composition of the municipal solid waste. So there are some problems associated with the MSW incineration residues due to the volatilization and subsequent condensation as well as concentration phenomena acting during combustion. MSWI residues have high concentration of heavy metals, salts as well as organic micropollutants. The fly ash is problematic for incinerator operation and can cause slagging and fouling in addition to environmental issues. The fly ash contains mainly heavy metals, a high content of easily soluble salts, and in some cases polychlorinated dioxin and furan. So what will happen if we are going to leave this fly ash as a uh, landfill material, okay, or if we are going to use it in the landfill, so what will happen, these mainly contains some heavy metals which can be easily water soluble, and what will happen during the landfilling, the water will react with these heavy metal contents, and those heavy metals will go into the water bodies, and that will again affect the health of the humans which are using those water bodies. The quantity, quality and characteristics of MSWI residue depend on the many factors such as the composition of the feed, types of incinerator, operating parameters and pollution control techniques. In some European countries, great efforts are devoted to utilization of such residue through various treatment processes. And if utilization is not possible due to regulatory constraints or any other reason, these residues have to be disposed in an environmentally acceptable and economically sustainable way. So, some treatment processes of bottom ash as defined here. Separation process. Separation is simplest treatment principle and may include both physical and chemical processes or a combination of both. Like we can separate the silica or iron values from these bottom ashes. Then particle size separation and magnetic separation is universally used where MSWI bottom ash is processed for utilization. The bottom ash typically contains 7 to 10% of scrap iron and 1 to 10% of non-magnetic metal. So this scrap iron can be easily uh, separated out with the help of the magnetic separation process, because scrap iron will be having magnetic properties. Then we can go for some thermal treatment process or treatment of air pollution control residues. So there are some different types of construct. So there are some engineering applications also for bottom ash. We can use the bottom ash content as a road construction material. Bottom ash substitutes sand or fine aggregates in road construction either as partial or full replacement due to its similar properties to the natural sand with uh, because it is containing around 30 to 40% of silica material. Bottom ash can be used as sub-base, road base material and bituminous mixes for binder layer. Bottom ash provides adequate bearing capacity for lower strength applications such as sub-base materials and embankment fills. So it can also be replaced as a aggregate replacement in the concrete material. Bottom ash can be used as either fine or coarse aggregate replacement. The replacement will cause some changes on the properties of concrete such as the workability, compressive strength and durability. And there are some utilization of fly ash material. So it can be used as a solid soil stabilization material. It is the physical and chemical alteration of soil to enhance physical properties. Usage of fly ash for soil stabilization increases the shear strength, controls the shrink or swell properties of soil, and improve load bearing capacity. But before these, the utilization of soil utilization of fly ash as a solid stabilization material, we have to remove the heavy metals from that fly ash. Then waste treatment, fly ash can be used in combination with other alkaline materials to transform sewage sludge into organic fertilizers or biofuel due to its alkalinity and water absorption capacity, because it contains high amount of calcium and magnesium, so it can be used as a basic material due to it which has a very high alkaline content, and it can be used as a water absorption. It can be used as used to treat the water waste due to its water absorption capacity. So now we will